All right, folks, let's go ahead and get started. We'll do multimodal models today, and we'll continue with the fusion models on Thursday. So that will cover a lot of the non-tech stuff that we're going to be doing in this class. A bunch of logistics. So homework 3 is going to come out soon. I released the project information. You can find it on the website, although there's nothing super magical in there. Homework 1 we finished grading. We'll put those grades up on Canvas in a second. I think basically everyone got 100, so it's not anything too complex. We are working on homework 2 currently. I'm not sure how many homeworks there will be in total, either 3 or 4. I'll let you guys know before, of course, the end. So we're also kind of approaching the end. We have 2 more weeks of this class. So we'll do 2 lectures. These are the ones I mentioned on non-text kind of stuff. And then we'll talk about scaling laws, which are a good kind of practical, how do you build these systems type of thing. And then kind of a grab bag lecture at the end, which is going to be Thursday next week. Afterwards, we'll all do presentations. And then we'll kind of keep going with that for the end of the class. There'll be presentations, your guys' project, homework assignments, and that'll be it. Any questions about logistics? All right. So let's go ahead and get started. The plan for today basically is to start off by talking about multimodal models very broadly. So we'll talk about a little bit of the history for it, even before sort of foundation models and large language models were a thing. We'll talk about some really simple adaptations of transformer-based systems like BERT to incorporate especially image modalities. And then we'll talk about kind of like very simple ways of using vision with transformer-like principles. And that's going to be a model called the VIT. Afterwards, we'll talk more about different kinds of vision language models. There's a whole bunch of these. And then finally, we'll look at other domains as well. So things like how do you incorporate audio, video. We've already seen code, so we're not going to spend too much time on it. And also things related to robotics, where basically you want a foundation model, but it's also operating a robot or things like that. So there's kind of a physical component to it too. Cool. Let's start with this first part. So here's kind of my incredibly short history of multimodal models, which is, you can guess, are not super, super new. So they predate foundation models, and you've probably seen some of these, right? So things like image captioning models, right? You plug in an image, the output is a text sentence that explains what's happening in that image. So that concept is super old. You've seen it for almost 20 years now. Visual question answering, VQA models, et cetera. So all these things really predate any kind of current foundation models. But not surprisingly, foundation models being powerful, you actually have a lot of popularity for these things. Let me show you one example that I do kind of like for what you could do even 15 years ago. So this is a nice paper that is from Bengio's group, but all the way back in 2010-ish. Essentially what they're doing here is trying to figure out how to do image captioning, but in a really simple way, where you're just trying to figure out whether words from some large vocabulary are associated with the image. And they kind of have a couple of baselines, right? There's a baseline that's sort of okay. It does pick out the right answer most of the time, or at least something that's in the image. But it also has a lot of other random stuff that's not really relevant. So in other words, it's kind of guessing and looking, but it can't say too much about like what's good and what's not. Their technique, which really is pretty much what we'll be talking about, align embedding spaces for the vision component and for the text component, it does a much better job of picking out a bunch of like relevant things over there. Even when it's not getting it exactly right, it's getting very closely related things, right? So over there for those dolphins, you get dolphins, orca, blah, 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 all relevant terms, which is not really the case for that one versus rest one. OK, so we're not going to spend too much time on like looking up these old techniques, since we have much more powerful things that we can do. But the basic idea, which is, hey, I'm going to take a vision encoder, get embeddings from it. I'll take a text encoder, get embeddings from that, and try to make those embeddings line up, right? That's basically all you really need to do. And most of the models we'll talk about today are going to be based on that principle too. Everybody OK with this? Cool. All right, so let's talk about kind of a version of what we've been talking about this whole time, but that also incorporates, for example, multiple modalities. And maybe the representative example that we'll focus on is this thing called visual BERT. And it's exactly what it sounds like. It's like BERT. And recall that we talked about BERT about a month ago. And it's going to just take in images in addition to text. So rather than producing embeddings and using them for various NLP tasks, we're now going to produce embeddings for images in text and then do various tasks with that. And these tasks could involve both modalities or just one or the other or whatever we like. Okay, so the first question is, how could we plug in images into something like BERT? What is the normal input to BERT? Anybody? Oh, sorry, yeah. Yeah, text sentences, right? Like a list of tokens, that's the normal input. So if we're going to incorporate an image, we also need to incorporate some notion of what is the equivalent of tokens from those images. And the thing that's annoying here, right, is that we don't necessarily know what could serve as a token from an image. For words, token sequences do represent sentences, but for images, they're not really sequential per se, right? So what these guys did is kind of the simplest possible thing. Go ahead and grab a model that will do image detection. And the image detection model will just say, here is a bounding box for something that's relevant in this image, right? And you can do this more than once. You can get a bunch of bounding boxes, all of which extract some information from the image, some part of it. And then you can go ahead and run an image embedder on those guys. And that will give you a vector. And that vector now becomes the equivalent of those token embedding vectors that we use as input to BERT, right? So here's kind of the picture for it. What you're seeing on the left over here is exactly what we would have from BERT. It's just taking this sentence, which is a person hits a ball with a tennis racket. You tokenize that sentence. You have a sequence of tokens. Those tokens get embedded. We add our positional encodings, blah, blah, blah. But basically, we have these different vectors that correspond to tokens for that sentence. We're also going to pass in the image. And we're going to do basically the same thing. I've run this image detection model on it. It's extracted these 4 pieces that you see over here. So this is the stuff that's relevant in this image, at least according to this image detection part. Maybe it's wrong. Maybe we're losing some information. That's all possible. So we're going to take this stuff, embed these guys with just a standard image embedder, and then we treat those things as if they're the word vectors, right? As if they're the token embeddings. And we just have a sequence of them. Now, exactly the meaning of this sequence is not super relevant, right? It's just whatever we got from this extractor. But it can be treated as if it's a sentence of these little image patches that are relevant. OK, everybody OK with this idea? Cool. So all we'll now do is pass these guys in exactly the same way as we did with BERT. All of it goes into a transformer. And then up top, we can do whatever we want with it. If you recall the way BERT worked, we had the CLS token. And we used that to sort of extract all the relevant information. And then we could build some kind of predictor head on top of that, fine-tune it, do whatever task we were interested in. Same exact idea now, but we can do tasks that involve both the caption and the image, right? Because we have access to both of these guys. And we can fine-tune this model to perform whatever it is that we're ultimately interested in. OK, everybody OK with this idea? Yeah, it's like a token embedding. So I have these 2 auxiliary models. One is first saying, show me the relevant bounding boxes, whatever number of them I want. Afterwards, I take what's in those bounding boxes, and I pass those things through an image embedder. That gives me one vector. That's the representation for that part of the image. And then I treat all those guys as if they're token embeddings. And I pass them into BERT. I use the full context window. It now includes both token embeddings for sentences and these little image embeddings that I got from my image.
There's no vocabulary associated.
There's no vocabulary. That's correct. I directly jump to using a function that performs the embedding rather than my big embedding lookup table for tokens. OK, this sound OK for everybody? Go for it.
Is there any vocabulary for letting you know that it is an image specifically? Like, let's say there are, let's say the tokens have feature vectors that are d-dimensional. You only use some number less than d to represent the actual image embedding, where the remaining tokens signal that what you're looking at is an image embedding?
No, we wouldn't want to do that, right? So I mean, we can certainly create special tokens that say, hey, I'm going to do something with this position that involves images. And that would be the equivalent of the class token that we put at the beginning, right? But that doesn't, we don't have to do anything to each of these different vectors. In fact, we wouldn't want to, right? We'd lose information by doing that. In fact, the game here is really to treat them as similarly as possible, right, to the word embeddings. They're just going to go through transformer layers as if they're the same thing, because we don't actually care about the modality. We're really getting rid of that almost immediately. Cool. So this is something very simple. It's kind of the simplest thing you could do to adapt something like BERT to perform image/text tasks. And you can imagine you can do this with other modalities too, right? It doesn't really have to just be an image. I could do exactly the same principle of a video. Now, granted, the equivalent of the bounding box would be more complex, but I could do it, right? People have done this exact thing, for example, with knowledge graphs. They say, hey, let's embed all the nodes in a knowledge graph, and then we just use them as part of this BERT-like procedure as well. So you can really do anything you'd like here. This is a pretty general principle. Other folks who have questions? OK, let's see another example of it. OK, so we took all the ideas from BERT. We added images. One question we might ask ourselves is, well, what do we do for training for BERT? Because we have to lift that training principle to this multimodal case as well, right? So how did BERT training work? OK, let's not recall both tasks and the full loss. What was the simplest thing that we did for BERT? Well, we did this thing called mass language modeling, right? We took particular positions in my text. We covered them. Of course, we know what the ground truth word is that's supposed to be there. But then we said, hey, let's go ahead and predict this masked word by looking at all the other words. And we said, hey, let's train the model until we can do that kind of prediction correctly. The representations that come out must be very relevant. They must contain all the useful contextual information. Same principle here, basically. We're going to do mass language modeling, except we're not going to really do anything with the images. We're going to put them in there, but we're not going to go ahead and train on them. And what's the real reason for this? Well, we don't really have a simple principle of predict the correct kind of token here, right? So this is getting back to the question of vocabulary. If I did have some notion of image vocabulary, I could mask the image patches as well. But here we don't, right? So we don't do anything. We're not going to try to reconstruct the missing part of the image. We're just going to leave the image be and hope that it's relevant. OK, everybody OK with this? So what kind of tasks should we actually do to connect the image component with the text? Things like sentence image prediction would be, right? So you do stuff that helps you use that image information, but you're also simultaneously learning stuff about words as well, just like we did in BERT by itself. And this turned out to work pretty well. It can figure out very quickly like all the relevant stuff. Different layers start representing different concepts. People figure out very quickly. So the low-level stuff, you're kind of seeing it over there, and kind of more abstract stuff as you go. So here's all the relevant bounding boxes for this fairly simple kind of input image. OK, now what's hard here? I mean, you're completely sort of determined by how good your initial image detector actually is and how relevant all those bounding boxes were. If you miss stuff at the beginning, there's really not that much you can do here, right? You have these auxiliary models that you're dependent on. OK, so let's see if we can solve that problem in particular. And let's see what we can do with image embeddings in general. I mean, the classic way is let's use something like a ResNet, very powerful CNN that was trained on something like ImageNet. And then you can use it to embed anything you like, right? But we've been spending all this time developing transformers. So let's see if we can do something kind of more clever, potentially, right? Transformers made a big difference for text. Maybe we can use some of those principles for images as well. And the model that we'll talk about is called VIT. I took this snapshot from Google Scholar like a long time ago. But as you can see, it's a paper from 2020 that already had like 50,000 citations. So this is kind of one of the biggest CV papers in the last 5 years. I'm sure someone can check because it's probably much more than that currently. OK, so let's see how it's going to work. As before, we really want to stay as close as possible to the basic transformer idea. So we should figure out a way to take our images and make them into something that looks like a sequence. And what's the simplest possible way of doing that? To, not surprisingly, just split up your image into equally sized patches and then make them a sequence, right? And that's basically what we're doing here. Here's our original image. This is, I don't know, Italy or somewhere like that. Split it up into parts. the parts are not based on, here's something that a separate model found relevant. It's literally just partitioning it into patches. These patches are fixed size. We can determine what size that is before we design the model. We're going to go ahead and just grab all of those things sequentially, right? And now we have what looks like a bunch of tokens. And these guys are going to now go into a linear projector. That will produce embeddings for them. And the only thing that we'll do in addition to this is give it some sequential information, some ordering information, which of course is exactly what we did with words as well, except now we're taking it from the location in the image where you're at. But it's the same exact principle, right? Nothing has really changed. OK, now we pass this guy through a transformer encoder. And then we'll have some MLP head at the end, if we want to do prediction, for example, the same way we would with a ResNet. And then we go ahead and say, OK, well, we'll predict classes as before. So this architecture looks pretty different from a convolutional neural network, at least at first glance. It's using the same principle as what we did for something like predicting something about a sentence with a transformer, but it's operating it on image patches instead. Otherwise, not really much of a difference. And finally, note that it's very BERT-like. This very first 0 position here is going to be the equivalent of the class token. So that part we don't take from an image patch. We keep that position for making our final prediction. That's where the embedding that we get at the end is going to go. That's the thing that we'll run our MLP on and what we'll use for making our prediction of the class. So think of this as something like some combination of like a ResNet with a BERT kind of principle. Everybody OK with this? All right, so what goes into the actual transformer block? Pretty much exactly what we did before, right? This is our standard transformer. We're not really changing anything here. And we're just passing these embedded patches into it. There's nothing else but that. Cool. So fairly simple architecture that just takes this transformer idea and applies it to image patches instead of words. And this turns out to actually work really, really well. OK, everybody OK with this? Yeah.
So for training this, will we do the same sort of mass training that we do for the original BERT?
So the answer is we have options here, right? It just depends on how we want to use this model. If we run this model in supervised mode, then we would train the same way as a ResNet, right? Train this guy on ImageNet, for example, right? Then it's supervised training. There's no self-supervised masked anything. But of course, you're right. We could do self-supervised training here in different ways as well. It just depends on what we're trying to get in general. So for example, I could take this thing and use it as the vision encoder in CLIP. And then I would be doing contrastive training for this guy, et cetera. The version I'm showing here, though, this is the supervised version, right? It actually has a head. We can train on it. Cool. Good question. All right. Everybody else OK with this? Go for it. Second.
Linear projection layer is a trainable layer.
Yeah. Everything here is trainable except the original patches and their raw pixels, right? Those are given to us as the input. Everything else we're going to train. All right, so the main thing that we got by looking at this guy is that the previous model that we had, it required obtaining those bounding boxes, and those were the relevant things. Now we don't have to do that, right? We could run a VIT, and this VIT basically would do the same job as what this model is trying to do. And in fact, we could just incorporate this into something that looked like BERT altogether. So let's try to do that next. Here's a model called VILT, just to be annoying, right? So it's like a VIT with a language component. It's going to be very similar to that visual BERT example. It's, in fact, exactly that, right? This is a very similar architecture to what we saw before. We basically said, hey, we're going to do BERT, but the context window will have both word embeddings, and it's going to have image embeddings, except now the image embeddings are coming from my VIT, or a principle that's very similar to the VIT itself. So just as before, I have my initial tokens for the words. I pass them through the word embedding layer. I go ahead and obtain these guys. Here I have these linear projections, which are what we did for the VIT. I take all of them, put them together into a transformer encoder. And then again, I can do training through whatever principles I want to do. But I'll always have some tasks that I'm training on that connect the images with the text. I'll always need that connection. Otherwise, there'll be no way to have them kind of communicate with each other. So some of the examples that they're doing are image text matching. just like we saw for CLIP, for example. Mass language modeling still for the words by themselves, because you want to learn about those words. Things like word and patch alignment, right? Which part of the sentence corresponds to which of the image patches, for example. All right, so these are some examples of tasks that we can train on. Some of them are single modality, unimodal. Some of them are multimodal. You definitely need at least one multimodal training task, or you cannot get alignment to kind of have these things correspond. Okay, everybody okay with this? So we're still predominantly trying to use the basic ideas, like things like BERT, but trying to incorporate image information or other modalities. And we're trying to make the fewest changes that we possibly can while still have everything kind of still work nicely, which these things do. Cool. Questions? Yeah.
I had a question about the positional embedding, because the word embedding, you only have one dimension, which is just, which position it is. But then
Yes.
if you have images, it's two-dimensional. You have X and Y
Yep.
axis. So how do they embed two different types of positional embedding?
Great question. Can we modify our standard positional embedding approaches to incorporate two axes?
Yes.
Yeah, that's basically the answer.
So for the word embedding, they just have, like, let's say the Y-axis is just kept zero.
Yeah,
Okay.
yeah, exactly. So nothing too scary happens here, basically. Okay, so simple idea for how we're going to use vision transformers plus BERT-like mass language modeling. That's this VILT model. Okay, question for you guys. Does anybody use these things currently? Well, the answer is not really, and we'll see some further examples. Basically, much more large-scale foundation models have really subsumed these kinds of models to the point where there's no really strong reason for you to sit down and train a VILT rather than getting very high-quality embeddings from a much more powerful foundation model. And we'll see something that looks closer to those powerful foundation models as we go. Okay, that didn't stop people from trying all this stuff, right? So here's a huge list that I got from a 22 paper. You can see basically all the different variations that people have tried, right? So all of those, starting from Visual BERT all the way down to VILT, are between 2019 and 2021, right? So this idea was extremely popular. People tried every conceivable variation. Right, you can see different text encoders, usually from BERT, but also other ones. Right, vision encoders starting with CNNs. When we didn't have VITs yet, we had to use standard convolutional networks. But then later, moving on to VITs. Then the question becomes sort of how do you fuse these together? And there's a bunch of different options. And what do you train on, right? So you have your choice of mass language modeling plus other. And then finally, what kind of data sets you train on? And these are sort of a lot of the multimodal data sets. So really, people have explored this idea to a huge, huge extent. But as I said, most of the time, we're not using these kinds of models anymore. Cool. All right, so let me show a couple more things. So data sets, you do need something that has images and text combinations, right? Again, if you never have images coming with text together, you have no way of understanding how to connect the vision representations with the text representations. So we'll always need these. This is sort of like what people have done in the past. If we go all the way back to sort of early 2010s, you actually still have quite a large number of image-text pairs that you can get from the internet. But over time, we've tried to get more and more of these. CLIP is much more modern, and CLIP has this proprietary data set of 400 million image-text pairs. The current standard are these data sets like Lion 5B, which is 5 billion pairs, and it's open source. So the amount of this kind of data that you have access to is actually very large now. But it also means that it's unlikely we can train our own model that's going to be too performant at home compared to closed source models. Another kind of variation is that people are starting to introduce a bunch more languages. For a long time, a lot of these multimodal data sets were really English only, and that was pretty restrictive. Increasingly, you can actually get almost any language there as well. Cool. I'll stop here for the beginning part, but I can answer any questions folks have. And if you don't have questions, feel free to hang out for a few minutes. Yeah, I mean, I shouldn't put it that way. So here, basically, we're using a VIT-like principle rather than initializing it. Pretend this part didn't exist, right? Then this would be a VIT. So we're just sort of adding a piece there. It's not, yeah, I mean, it's not technically initializing it that way. But I could build a model where I literally did have a VIT and then BERT, and I fused, right? And that would be that. Go for it.
The way that they like split the image into like section, static boxes. I don't know, it just seems like kind of crude.
Yeah, that's exactly right. It's sort of like thinking about attention, right? It's very crude. It just says, hey, look at every pair, right? And see if there's an interaction there. It just turns out that this captures more information, and anything more smart is actually worse, right? That's sort of the story of a lot of our class here. Don't try to be too clever. Just do the stupidest thing first and see if it works well. The other piece that's nice is it's very scalable, right? It's not hard for me to take any image whatsoever and just split it up into patches and keep training. But there is a lot of work on like, okay, how big should the patches be, right? Like what order should I present them in? Like all these factors make a difference and people study them pretty intensively. Yep.
How do we tackle the patch embedding? Because in case of tech,
Yeah. Same principle. I can modify any encoding scheme that's unidimensional to a two-dimensional version. Right? There's nothing really stopping me from doing that.
okay, so we can probably like do the same thing how we do in text.
Yeah. There's also a ton of these. People use different ones. But like I said, just adapt a one-dimensional scheme to two dimensions, and you always have that trivially.
You mentioned about the bounding boxes, right?
Yep.
So, like, do we train them to get the bounding box important?
No, we have a separate model. That separate model is frozen. It says, here are the relevant bounding boxes in this image. And then we take a fixed embedder, like a trained ResNet, and we embed each of those bounding box parts. But that part's not trained, right? It's frozen.
So in this way, trying to get the embeddings of the first, like the bounding box part. So if you already teach it, how do we get the embeddings of this image?
We're getting embeddings of parts of the image that some external model thinks are relevant. And those embeddings are coming from a frozen model, but those embeddings are used as if they were the word embeddings for the input to the transformer layer. So those are the things that come just as if they were word embeddings. They get passed into the transformer, and the transformer will do things like self-attention and so forth.
I have a question on this thing. So,
Yep.
are we trying to like have some kind of padding or kind of that like to concatenate the word embedding in the image embedding? So, like, are we training them like in?
No, you put them together pretty much. You treat these as if they are just a sentence, right? Except the sentence now has visual components. And these visual components are just these patches from the image. Now, you do have a separator, right? Because you always have this special symbol, this star guy. That's like the equivalent of the CLS token that you have for the sentence. So it's not like the model is confused about where the image part starts. It knows. But it doesn't have to place them in some fixed position here.
Okay. And are we also like masking the image embeddings, or like are we only masking the word embeddings?
It depends on how we want to train this model, right? Normally, the answer is we only mask the word parts, and we depend on something else to align the word and image patches, right? But we also could do that. And there's models that also just do masking and reconstruction of the hidden patches, basically. I just don't think this one does that. I think these are their three sort of tasks that they're looking at. Yep. All right, we can keep going in like 1 minute. Okay, let's go ahead and get started. So what we did for the first part was just kind of a very brief introduction to how you would modify standard language modeling principles to incorporate this extra modality. And it was just vision, right? But there's nothing stopping us from doing anything else. Now I want to talk a little bit about different variations for VLMs. And of course, these ones as well, we could lift to other modalities in pretty much the same way. So let's talk about sort of what we do for multiple encoders. We really only had one encoder so far, right? We were basically treating that transformer as if it was just taking all the possible inputs and encoding them together. But we don't have to do it that way, right? We can have two separate encoders, and we already saw a model that does this. That was CLIP. So we'll talk about contrastive training like CLIP. We'll talk about joint training. We'll talk about different forms of what's called fusion. And then we'll kind of move on to sort of more complex use of these modalities. So far, a lot of what we talked about is here's one piece of text, here's an image, do something, get some relevant embedding, use that to make some kind of prediction. But if we want to do things like generative tasks that include both modalities, we'll have to get a little bit more advanced than that. So we'll talk about basically the original idea, which is few-shot models, and then visual instructions, which will kind of take us all the way to what are frontier models now. Okay, so let's get started with contrastive visual language models. So what we've talked about so far basically was, hey, we're going to train everything together. So text and images are both inputs to my transformer. And all I'm doing basically is tokenizing the text, splitting up the image into patches, treating all those objects as just elements of some big sequence, embedding those elements, of course slightly differently, word embeddings for the tokens, and then image embeddings for the actual patches, but otherwise they're treated the same. You pass all of that to a transformer and let it do its work. Okay, that's not the only way that we can do things, right? And what we're really going to talk about is let's change where we do this fusion. So here the fusion was at the input, right? We take everything, split it up, treat it all as one big sentence. And then everything happens upstream of that. But of course, we're not limited in the way we're doing it. We can change that fusion point to happen later. And for example, one way of doing that is, hey, let's do two separate representations, one for the text, one for the image, or whatever other modalities we have, and let's have some means of connecting them. In other words, let's find some way of aligning those representation spaces, but after we've actually produced the representations, rather than earlier on. So this is the question of where should you fuse signals? Early fusion, late fusion, somewhere in the middle, right? And this is kind of a design choice. There's pros and cons for all of these things. So what would be a pro of late fusion? Anybody have a guess? Go for it.
Depending on the latent space that you learn, you now have a generative model where you can put images into that model and have it spit out something in that auto-encoded space that represents the text as well.
I can do that, but I can do that with early fusion too, right? So that's a good point, and we'll actually do that. But that's not strictly between late and early fusion. I can do it in both cases, it's just slightly different. Go for it.
The advantage of being just computationally more efficient is now you're compressing this information already. So like you have early fusion, you're just compressing a lot of information that's very early on.
Yes, that's basically the right answer. So the answer, of course, is computationally, it's cheaper to have two smaller separate encoders. But more than that, right? I can take those separate encoders from wherever I want. I can pre-train separately on the image and text encoders, and then I can do something to hook them up later. And I'll have to do that alignment piece later on, but maybe a lot of the training can just go into each of these two things separately. And maybe we can even just reuse powerful pre-trained models. So that's one of the advantages of late fusion. What's a disadvantage for late fusion? Sure, go for it. Yeah, I think you're getting to the right answer there. I mean, the more annoying thing is I have some fixed representation for the image, some fixed one, right, for the text. If I need some more complicated interactions between these two things, this just gets very hard. Whatever's in those two representations is the best I can do. And in fact, we'll see that things like CLIP really struggle. Like, they really do not track like interactions very carefully. So in clip, for example, you can tell that there's like a ball sitting on a chair, but things like, oh, are the balls on top of the chair or under? That's too late, right? It can't figure that out anymore. That's something you have to do much earlier on. Okay, so let's go see some of these examples. For late fusion, we'll use this contrastive approach. That's sort of the simplest way of training many of these models. But of course, we have other things that we could do as well. Okay, so let's see this example. We're going to start by talking about the particular loss function that we'll train on for doing this kind of contrastive loss. So this one, info NCE, is a fancy name. NCE is noise contrastive estimation. Not super important, but let's take a look at the actual details for this loss function. Okay, so what's going on here? I am going to minimize the negative log. If you minimize the negative log, that's the same thing as maximizing what's inside the log. So really all we're saying is maximize what's sitting there in this fraction. And this fraction is a softmax looking thing. I have an exponential of a dot product. Okay, so what's happening? I'm basically taking some images representation. That is what this Z superscript capital I is. Capital I means image here. The little I is just, hey, this is the ith sample from a batch that I have. Okay, and what am I trying to maximize? Well, I want to make my numerator large if I'm maximizing the inside of the log. So I want to make that top thing as large as I can. And what's happening over there with that Z plus? Okay, so this Z plus is going to be the image representation for another relevant similar image. For example, an image that has the same caption. Well, okay, where do I get these similar images? I could take the original ZI and mess it up a little bit, right? Change it, but not in any material way, right? We expect that things that I've kind of just changed a tiny bit should really have the same kind of representation, and therefore they should be relatively well aligned, which means the exp of the dot product should be high. Okay, now I'm going to normalize by all the stuff that I don't really want to be aligned, and that is to say all the other images in my batch, all the ZJs. So my denominator, right, I want to make it small. So in other words, I want to make sure that these things are not high. All right, everybody okay with that? So I'm just saying, hey, similar things should be high. Distant things, dissimilar things should be distant. And that's really all that's going on here. Now, this thing by itself is really just operating on the images, right? It hasn't said anything yet about mixing up images and text. But there's nothing stopping me from doing that by swapping out these ZIs with relevant ZTs that are coming from the text encoder. So here's an example of that. Two functions that are just symmetric versions. And notice that now I have ZI dot ZT, and I have ZT dot ZI. But it's exactly the same thing. I'm saying, hey, things should be matching up when I have the image and caption from the same image. But they should not be matching up when I have an image and a caption that are from different things. All right, everybody okay with this? Okay, now I can just run this bottom part, for example. But the top part is actually also useful, right? It's another form of self-supervised training. The top part can be used to run an image encoder totally separate from anything to do with the text. And therefore, I can beef up how good my image encoder is. And I could do something similar for the text encoder as well, although that's less frequent in these cases. But okay, everybody okay with what we've been trying to do here? I sample a batch. I pick one element of that batch. I say, hey, either an image that looks exactly like me, or the relevant piece of text, the actual caption for me. Those representations should be very well aligned with myself. But other things should not be well aligned with me, whether it's other images or non-matching pieces of text. And that's what we're doing here with these loss functions. They look fancy, but it's really something relatively simple. Okay, everybody okay with this? All right, so what can we train with these kinds of loss functions? Well, the simplest one is the model that we already talked about a little bit, which is clip. So again, you're taking very, very simple principles and scaling them up to produce a pretty good vision language model. And it's exactly what we saw before. We're going to run that noise contrastive estimation, info NCE loss. And we're going to do it on exactly batches that are sampled from my data set, where I want to make sure that the matching image and text encodings are high in alignment, and things that don't match are low. So it's literally just the bottom part from here, but I'm applying it to a big image text data set. All right, everybody's comfortable with this? We've seen it already. Yeah?
The loss function, why do we have two losses, like I to T and T to I if we are training it?
Just to symmetrize, I actually don't really have to do that, right? I can just take one of those guys. It's just the problem then is like I'm always saying, hey, the image should be looking at all the text parts, but never the text with the matching image parts. So that asymmetry can lead to some weirdness in training, but if you symmetrize that way, you don't have that. Cool, so everybody's okay with what's happening in this picture? Which we've seen a couple of times now. Now, okay, one caveat here. When you look at this thing, you know, we're not really doing it at the level of the full data set. We're doing this process for batches, right? We're not going to be able to form a loss that is simultaneously taking in every non-matching image from the entire data set. So don't think of it as just this giant matrix. Think of a bunch of little sub-matrices here, right? Everybody see what I mean? This capital N is 400 million. I'm not in a position to train on a batch of size 400 million. At least, you know, not so far. Cool. Okay, so let's see some more advanced pieces than just clip by itself, right? So we talked about how we can really do sort of separate pre-training on just one modality versus the other, and we can do this fusion part as well. You can kind of throw everything in, right? Pre-train separately and jointly. So here we have a text encoder. We know how to do self-supervised training on a text encoder. It's just mass language modeling, right? Just as we've done before. Here we have an image encoder. Well, we know how to do various kinds of pre-training for image encoders, right? One could be exactly that NCE, that contrastive loss that we talked about. The other could be even supervised training, for example, on ImageNet or whatever we'd like. And then I can go ahead and do the combined version, right? Which is just go ahead and do contrastive training on these two parts simultaneously, or other approaches, right? And now I have this sort of model that's good for everything. I can do tasks that only involve language, only involve images, that are multimodal, et cetera. Cool, so this is one thing that we can do. Now this is all still kind of within this, I'm going to do something and make a prediction, right? It's not generative. In the same way that BERT was not a generative model, for discrete NLP tasks, it was the most powerful model. But if we wanted to do anything that involved, for example, chatting with the model, we couldn't use it. So same problem here. We'd like to move toward that more generative setting, and therefore we'll have to sort of change some things, at least with our design so far. Everybody agree? All right, so what's one thing that we can do in the generative setting that we'd like to do in these multimodal cases as well? Can I ask a question of clip? Like, can I say, hey, what's in this picture? Describe it to me. No, right? So I need some real language model, some generative language model component there to enable it to do that, right? So this is really getting closer now to what the state of the art is. Let's talk about what we're going to call few-shot VLMs. They're sort of the origination for what people are currently doing. All right, so far we've seen things like, okay, do zero-shot prediction or be fine-tuned for some particular tasks. But let's see if we can get a little bit closer to what we did with language models. Even for language models, right, we can do zero-shot prediction, and we can fine-tune them to do one particular task, but we didn't want to, right? We wanted to do inference time things like, hey, ask the question, get an answer, ask another question, and so forth. And of course, we can do exactly that kind of thing for images as well, right? So here's a really simple example. This is literally in-context learning, but for a generative type vision language model. So this is far more advanced than anything that we've seen so far. None of the models that we've seen yet can handle this, but here's some of the things that we're seeing, right? We pass in, for example, that image over there, and we say, oh yeah, this is a chinchilla. They are from a certain place. We show them a dog image. This is, you know, whatever, right? So we could say, hey, afterwards, this is, and let it fill in the blank. And we'd like it to follow the same pattern that we see on top, name the animal, and then say where it's from. So as you can see, this is much harder, right? It's doing everything we did for language models, including in-context learning, and it's trying to say, okay, we'll do that now, but incorporate images as well. So it's even more complexity. Same deal here. It's saying, hey, what's the answer, right, to the painting, or where is it located, or things like that. This is a Van Gogh. Same deal, right? All right, so what should we do to build a model that can do this? All right, let me ask it differently. What's one component that we'll need for sure? We'll need a vision encoder, although that's what we've already had. So it will be a new component, right, that we haven't dealt with so far. Yeah?
We'll need some way to make sure that the context of a specific image is paired with the associated text in the same single prompt.
We will have to do that, yes. And since we're doing prompts, what kind of model will we need? Well, yeah, we're going to need some generative language model, right? Like right off the bat, what you're seeing here is doing generative modeling because it has to be able to answer a flamingo, they are found in the Caribbean, right? So this is not something that our classification-based models like BERT can do. So right off the bat, we need a language model, and it better be powerful enough to produce this kind of answer, right? And as we've seen, even this would be not trivial with some of the earlier, simpler language models. So this is where we're going to get to something interesting. We need a powerful pre-trained language model just to be able to answer questions. And all of this stuff about images has to kind of be grafted on top, right? Because we are unlikely to be able to train our own model from scratch that has sufficient language ability to produce for you this answer, even if you told it what was in the image. Everybody agree? Like, we're going to need something like a llama level model right off the bat just to have the language ability. So really what this suggests is I need to start with a pre-trained model that is a language model, and every new capability I have to find some way of injecting it into this pre-trained model. But it's going to be different, right? We're not going to train any representations from scratch. We're not going to treat the language model or the language encoder as equal with the vision encoder. Here we really have to start with a language model component, and we really can't do too much to it, right? It's not something I can really pre-train at all. So everything we're going to do is going to start from that starting point. Okay, everybody see what I mean by this, by the way? And this is how you have to think about these things if you want to get these very powerful language style answers. You will always have to start with these powerful pre-trained models. Okay, so let's see a paper that was very popular. It's called Flamingo, right? So right off the bat, you can see that it's quite large. 80 billion parameter model, of which almost all of them are your pre-trained language model component. So this is always going to be the starting point. But then I can modify it to incorporate the things I wanted, which include things like this. I will now start including multiple images here. And to handle that, I'll need to have a slightly more complex architecture than anything that we've done so far. However, we'll get some pretty cool results, right? So notice that we're now talking about something very conversational, right? I can include an image. I can ask questions about it. I can ask follow-ups to those questions, exactly as what we did with large language models, except now I can throw in images whenever I want to. I can also throw in multiple images and ask questions about what's shared or related between those guys, for example, right? So here's a case where there's 3 flamingos, and the question is, hey, what is in common? They're all flamingos. So as you can see, this is something much more powerful, and therefore it's going to be a little bit more complicated to build a system that has these capabilities. But the key ingredient is still going to be start from your language model component. That's the part that you really cannot do without here. Okay, so let's see how we're going to build it. Here's the architecture. It's a bit richer than what we've seen before, but the principle is actually not too crazy. We are going to take some stuff that's sort of pre-trained and frozen, and we'll throw some new things in. And we'll find a way to do some amount of training on the new things that we've thrown in. It's just that those new things cannot be the full language model. Okay, so not surprisingly, we're going to have our language model. You can see it over there. We're actually going to do something weird, where rather than treating the full language model as one big fixed block, we're going to rip apart its components. So we're going to have different blocks, and then we'll put stuff in between those blocks. Now, this seems weird at first, but we actually kind of did this already. So for example, if you think back to things like LoRa or other adapters, we were willing to put in little modules of trainable parameters inside the layers, right? So we are already comfortable with ripping language model components and putting stuff in between. Now we're going to do it in a way that lets us do all of this kind of more advanced vision language kind of stuff. All right, everybody okay with that? So the model that will do everything for us is going to be over here. It's going to be this blue guy, and you see all the layers, first, second, third, up to nth language model blocks. We're not going to change those guys. They'll be frozen, which is good. I don't want to invest a ton into training those layers. OK, so I have those things. Notice at the end, I get an output. That's another token sequence. This is, of course, possible because these are generative model blocks. They can output sentences in the same way a regular language model would. So we're in good shape in that sense. Now let's look at how we incorporate the images. Well, basically what we're going to have here is a vision encoder. So far, so good. There's no difference between clip and this. And those vision encoders are frozen. They just give me representations of those images. So nothing special. Now I'm going to have an additional trainable layer. It's not really super relevant what those trainable layers do. They essentially resample elements from my image embedding, but it's not critical. And what I'll do is I'll sort of add these in and do another layer of attention. And this layer of attention will be cross-attention. So rather than treating everything as one big sentence and doing self-attention inside my transformers on that single sentence, I'll now be acting as if I have two different sentences. One sentence is language. The other sentence is my image parts, which can be multiple images here. And this new sentence is almost like, think of the translated sentence back when we did the original translation transformer. I was doing cross-attention on those, right? I was doing a layer that was saying, hey, attention for the old sentence, and here's attention for my new translated sentence. Same idea here, except now our sentences are text and these image components. And I incorporate these cross-attention layers right in between my language modeling blocks, which is basically what we saw as well when we were doing the original transformer. We just stopped talking about that back then. So this is the basic idea. Nothing incredibly crazy happening here. It's just sort of the adaptation you would make to permit having these sentences kind of go inside a transformer and then permit generative outputs as we did before. OK, and while I actually go ahead and train here, it's just these purple guys, right? So the cross-attention layers get trained, and then these perceiver resampler layers get trained as well. And this by itself actually works pretty well. The only thing that is kind of more annoying here is I do have to generate enough data to train this guy, right? If I just train it on sentences without images, I really will not get anything interesting out of it. I have to get enough of those kinds of examples like we saw here for me to be able to train this guy and get meaningful results out of it. So in other words, what are we really doing? More or less instruction tuning on this sort of slightly more complicated architecture where we've interspersed all of these sentences coming from vision encoders and kind of added them in with cross-attention. So kind of a long story, but ultimately, as you can see, it's actually not too much more complex than a basic generative transformer. We've just found a way to incorporate these image components. All right, everybody OK with this guy? Yeah.
I have a question with image tokens that are put to process text. Does image tokens index the specific image they represent?
Yes, they are. So there is some encoding scheme that tells you about like the order of the images and things like that. But I admit I actually do not know the details, so we should look those up if you're curious about how it works. Yeah. Yeah. Although we could also do it backwards, really, but.
You have like multiple images, you just concatenate them, they're embedded.
Yeah, so I mean, we're actually taking each of these images and taking all their pieces, and then, right, exactly, concatenating all of them, however many there are, right? Yeah.
I have a question about receiver resampler. So what's the point of having this receiver resampler? Why not just, I mean, like I would imagine it would be computationally expensive to just go from vision encoder directly to the cross attention.
You essentially will need something there to align these representation spaces, right, to get them to understand each other, right, even before you head to the attention parts. And really, you could put in other things there. this is a nice model that sort of focuses in on the right things, but we'll soon replace it with something much cheaper. What is the simplest thing you could do over there that helps you align these spaces? Right. So let's see if we can do that next. Okay, great questions. Anybody else have questions? Yeah.
So in this image though, when it is translated, we incorporate the information of that image embedding.
Yep. And we can have multiple of these image embeddings, right? We're going to get a bunch of these guys. We'll treat them as kind of a separate sentence. That separate sentence has something relevant to say to our current sentence that we're generating, right? And therefore, we'll run this cross-attention process on it repeatedly in between all the blocks.
We have supervised the training or semi-supervised?
It's essentially supervised, right? Because I do have sort of the right answers or useful conversations to train on, right? And if you don't have that, this becomes a very difficult process. So think of this as close to instruction tuning, like post-training type stuff that I do for my language model. Okay, so let's talk about another similar approach. It's also visual instruction tuning. And this is a paper that, well, was built by our department. So this is Yangjae's group. It's called Lava. It actually very quickly became the most popular open source model of this type. Very similar, right? We're trying to experiment to figure out whether an open source model that we build, and essentially building on top of an open source language model, like a llama, is it really capable of something similarly close to something like GPT-4, which has kind of native multimodal support? And the answer is yes, but we need some architecture that's, one, simple enough and scalable enough. And here's basically how we do it. It's very similar to Flamingo, except in this case, we're not going to do that perceiver business. We're going to say, hey, take my vision encoder, right, for my image, go ahead and run a trainable projection layer, and then plug it in as a token into my token sequence, add that into my frozen language model, and let's go ahead and train. So this is a very simple architecture, but the nice thing is it's really quite scalable, right? I don't have very complicated models that are modifying the vision encodings. And let's see some examples of what the data looks like. Right, so we're going to do, ideally, a bunch of fairly complex and challenging questions, train on those, and then we'll evaluate on even harder things. And this is a cute example that I like from their paper. What is happening over there that's difficult for a language model for a person to understand? Right, maybe the image is too small. OK, it's maybe not that funny, but it is amusing to me. And I mean, these are the kinds of things, right, that like people who do self-driving have to really care about. Like absolutely bizarre stuff that is not that easy to think of, but can show up, right? So what we have here is a man attached to the back of a car that's ironing his shirt. And this is going to be very confusing for a model. So let's see what our models are capable of, right? The question we're going to ask is, what is unusual about this image, right? We're going to see different models, including Lava, right, trying to answer it. This is actually a pretty good answer, right? A man ironing clothes on the back of a minivan, which is not something that would happen, right? And indeed, you can actually continue and get more samples of this kind of, this kind of question. Notice that GPT-4 can also kind of do it. But look how bad some of these earlier models are. A man sitting on the back of a yellow cab, right? Open Flamingo is also pretty decent, but drying his clothes on the hood of his car is not correct either, right? So basically, a lot of this stuff really comes down to both what is your architecture, can you train long enough, and most critically, can you get good data that really forces the model to be able to do a good amount of visual reasoning. However, all of this said, it's not a fully solved problem. Both closed source and open source models often will still fail on examples like this. And it's also kind of like whack-a-mole, right? Once you've built a bunch of these examples, people will train on them. You'll get better on benchmarks. But then when you actually get some new out-of-distribution kind of images, it can still be very, very hard. OK, so let's take a look, for example, at even more powerful models. These are closed source, right? So we don't have access to their weights. We cannot build on them. We cannot modify them directly. They do fairly similar things, though, right? Now, one distinction here is the following. Closed source models do not have to first pre-train a language model and then incorporate the extra modalities like images. They can train from scratch on both simultaneously. So they don't have to do this kind of late fusion modification business. They can make other modalities basically first-class citizens. And that will make them at least slightly more powerful overall in general. Now, why can't we do this? Well, again, it's too expensive, right? I cannot come home and go and say, hey, I'm going to train a language vision model, even like a Lava, from scratch, because the language part is just too expensive. You can see what these things can do. They are increasingly very good. For example, you can take a handwritten problem and ask the model to basically read the handwriting and go ahead and solve the problem. Now, this includes everything that we've talked about in the class, right? So it's multimodal. It has to have basically OCR capabilities. And then it has to take all that stuff and do reasoning on it, because this is a math problem. But these models can do it, and they've become quite good at it overall. OK, everybody OK with this? Yeah. Oh, so just optical character recognition? Like, yeah, this is just Gemini that you can access yourself, right? I mean, you have to pay for it. That's the only annoying thing. But yeah, I forgot who ran this example, but someone I know in any case, yeah. Yeah.
In case of Lava, we have this language model. We also have multi-headed engineers like Lava, right? And we are training those. Or
Just internally. So the language model has multi-head attention inside it.
so it's kind of a pre-trained way.
Yep.
The whole layer.
Yep.
And we are only training this project.
Exactly,
layer,
yeah.
And it's working.
Yeah. So I mean, it's interesting, right? But basically, the real reason for this stuff is, in the end, all of these concepts, yeah, they're in different modalities, but they express the same information. So if we do a decent job of aligning the representation spaces, it'll all be the same kind of latent information, and we can just work with it. Cool. All right, so I'm going to stop here for kind of talking about closed source models. Let's take our next break, and I can answer more questions if folks have any. All right, next question for you guys. Why can't I just go ahead and also produce outputs that are more than text, right? Like, why can't I ask GPT-5 to give me a video in response to my question, for example? Yeah, our class always has one simple answer for these questions. It's too expensive, right? So this is the kind of the annoying thing. Language models have gotten pretty cheap at text generation. But when we do generation for any other modality, things get a little more expensive. And although we can do it, and for example, GPT-5 has diffusion models that can give you image output built in, it's still slow, right? It's expensive. And for video, it's even slower, which is why we have separate models and a bunch of constraints on how often you can use them and how long you have to wait. All right, maybe we can go ahead and we'll see if we can finish in time. I think for the last bit, I wanted to also briefly talk about other modalities. We've been kind of hyper-focused on text and images. And that's sort of always the starting point, because 95% of the time, that's kind of all we need. But of course, we have other domains as well. So audio, video. Really, we've kind of already talked about code generation, but for a while, you could think of code as a separate type of modality. It definitely has different properties than just kind of raw text. And finally, robotics via RL. That's sort of the other place where we can have our models do stuff. The other modality in that case is, for example, our inputs could include sort of sense information about an environment. And our outputs could be things like taking actions, right? which again is a very different kind of generative output compared to just language. So we use foundation models for all of these things. It's just that these are slightly less common than everything else that we're talking about with image and text. Okay, so for audio, it turns out basically audio is not that different from images. And why is that? Does anyone have a guess? Yeah.
I think it's like an ECE thing, but you can take audio and then do convolution, and you have the, I forgot the specific name, it was like the spectrum thing, and then
Yeah.
essentially treat it as an image.
Okay, we'll accept that. That's the EC thing indeed. Yes, I can, right? I can take representations of audio, right? Like, for example, the spectrogram that you're seeing here, so your terminology is right as well. I can more or less treat this guy as an image, right? And then I can run convolutional layers on this type of thing. In fact, that's where convolution indeed came from. In the original kind of sense of convolution, it was just part of filtering. So we can do this, and then we can go ahead and kind of pass this, as before, into any of our transformer kind of layers. And we can treat this thing as a sequence as well. Nothing is different here. In fact, audio is very much a sequential thing when we go ahead and sample it. And that's what we've been doing kind of for signal processing forever. So this is kind of a nice example. Whisper is a very large data set from OpenAI and a corresponding model. They got 700,000 hours of audio. And for this audio, you also have things like transcripts, right? You have the text explaining what was going on in there. So you can do cross-modal kind of training in these cases. And this is just a very powerful model that can do all kinds of things, right? You can do things like go ahead and do transcription, right? You listen to someone speak. You produce a text for it. That's very natural. You can do direct translation, right? You start in a different language for the speech, but the words you get are actually in the next language you're interested in. You can do things like say, hey, can you detect if there's speech or no speech? Pretty much any audio task you would like, this kind of model can handle this kind of thing. You can, of course, incorporate this with video as well, and there's nothing stopping us. So this is a system that was called Merlot. It's from folks that were at kind of AI2 and University of Washington. As you can see, this thing is getting a bit more complex. It was built on YouTube videos that also have transcripts explaining what's in them. But in principle, it's basically the same thing. It's we're going to take our videos, split them up into frames, pass those frames through our image encoders. We'll still have our language model component that is taking words and embeddings. And we'll have this kind of big BERT-like thing that is operating on video plus on our text. And then, of course, we can add audio to this thing as well. All we'll have to do is to make sure that we're kind of making sure all those pieces match up, right? The frames are happening at some step in time. The transcript for it, the text, is also happening at some point in time. We'll have to kind of make those match up. And we can do that contrastively, right? So that's what you're seeing on the left, contrastive frame caption matching. But really the same principle for what we've seen so far. Okay, now the kind of annoying thing about a system like this is, again, it's going to get very expensive to train, especially on longer videos, because anything but very short videos have many frames, and this thing can ultimately get very costly as a result. We can also do sort of non-frame-based video. There are ways of directly encoding a video rather than a sequence of frames. All these things have been tried at different points. All right, so I have this original slide for codecs, but just as a warning, again, we don't really have quite as many sort of dedicated code models anymore. Code has now just been incorporated into our standard language models. But we've actually seen codecs before as well, right? So we started with GPT-3. We fine-tuned on it to give it coding abilities. And this is when we were talking about human eval as that sort of programming problem kind of data set. But for pre-training, right, you get a ton of Python files, right? So really a huge amount of these that are coming from places like GitHub and are public. So you can get your model to understand code by just showing it all of this stuff. You do some pre-processing, you remove some stuff that's annoying, you kind of make sure that you have long enough lines, et cetera. And then eval is exactly what we talked about before. So this is codecs. We've already seen it. But this is, again, going to happen during mid and post-training for every language model currently. And kind of the first really nice open source model was called StarCoder, right, which was trained on a data set called the Stack that we'll talk about a little bit later on. But basically, it has lots of different programming languages. It has a huge number of tokens that you can pre-train on, including a huge number of specifically Python tokens. All right, let me continue. The piece that I think is most interesting here is the way that we'll be able to use foundation models in robotics here. And you can sort of, out of the box, do a little bit of this, right? So you can use language models for planning and robotics. Well, one thing that's annoying is that your foundation model does not itself know what environment you're in, right? So it's not what's called grounded. It cannot connect itself to what's currently happening in that environment. So much of this work is trying to figure out a way that you can mix foundation models or large language models with principles that are coming from robotics or RL. So let me show you a simple example, right? You could do something like the following. I spilled my drink, can you help? Can be my prompt. And I can ask a language model what to do. And you can get a sentence from the language model that may or may not be useful, right? So there could be things like you could try using a vacuum cleaner. That's a suggestion. Sometimes, I'm sorry I didn't mean to spell it, is a pretty funny answer. I mean, that's completely useless, but amusing. What we really want to be able to do, though, is can we translate these kinds of sentences or descriptions into a policy that if we were operating, let's say, a robot, we could actually go deploy. And now what's complicated here is that the policy only has certain actions it can take, and whatever description the language model gives you may not line up, at least not directly, with those actions. So what a lot of this research tries to do is to try to figure out some way of combining stuff that you get from an LLM, which is sort of high-level, common sense type of answers, then relevant pieces that we have, like a value function, that tells us how much we could potentially get from a particular action, line those two things up together, and try to combine them. And here, basically, it turns out, hey, find a sponge is the logical first thing to do. And we got this information from a language model plan, plus a trained value function that we got for this setting. So this is something very popular. We are going to run out of time, but I'll talk about it a tiny bit more. It's called SayCan. We're going to solve this problem of grounding. And the basic idea looks something like this. Here's a very simple policy, right? It has two components here. It's saying something like the following. First, I'm going to look at the probability of completing some state, some step from the current state I'm in. And then I have to incorporate what I get from my language model, which is the probability of this step actually being something that makes sense here. So I have some kind of policy that's using stuff that comes from more traditional RL, which says, hey, well, if you take these actions, this is what your expected cumulative reward is going to be. And something that's coming from the language model, which can figure out, hey, this is actually valid or not in this context. So we're going to combine these two things, and that's going to permit us to actually do a much better job than either of these two pieces by themselves. So this is kind of one way we can use a language model. Let me show you, an even fancier way. So for navigating with a robot, we now have a very complex potential environment, and we could really bring in foundation models that will address all the different senses that my robot could have. So I could bring in a language model, I could bring in a vision model, I can bring in a foundation model that specifically outputs actions, and I can handle all of these things. Here's one example that I quite like. So what's happening here basically is I'm building up a stack of different foundation models that are going to get different things. So for example, general instructions, observations from an environment, like my robot has a camera that it can take stills with, and it's going to go ahead and incorporate all these pieces into a map where it's looking for landmarks and trying to figure out the current location based on 2D images against landmarks on this map. And in addition to this, it's going to figure out what is a good path based on its expected location on this map overall. So again, we're incorporating all kinds of different modalities into here. We could have, for example, a graph that incorporates all of these different landmarks. We could have, of course, our language model that takes in text instructions. And we have our vision language model that's taking in these images that the camera on the robot is getting us. So now we have this sort of giant system that takes in every conceivable modality that a robot could use and uses these things to do planning and to figure out what actions it should take. So I'll say more about this next time because we are out of time. But this is kind of the full diagram for what we're going to do here. All right, let's keep going with this on Thursday. I'll stop there. Does it look complex enough?
I'm going to be honest, I lost it on this one.
We'll talk about it some more next time.
I think I'm just going to open up the slides and pre-train myself on this a little bit.
same feature that they use for Tesla auto drive? Because I know Carvajal mentioned once that they incorporated transformer for at least signal lines.
They do, yeah. This system is something else, right? This is an open source project from somebody. So unfortunately, it's unlikely that they're using exactly this kind of stuff. But I mean, the information you're getting is very similar. However, you usually in self-driving have even more signals, right? You have your LiDAR, you have things like that.
I don't know, what should self-driving car do when it sees a man doing his laundry on the back of another cab?
It is.
Maybe